have to send me an email. So my address should be on screen when I give these instructions. And the people, yeah. So when we start the transmission.
Yeah,
Yes, we are already live on YouTube. But let's be fair. In my watch, still 2 minutes to go, so let's not start before.
Oh yeah, there's no hurry.
So during this visit, we were at our normal seminar room here. So if you were here, you would be probably there or in an auditorium at IMPI. And what's going to be missing is the biscuits I normally offer at the end. And yeah.
Yeah, you guys were very gracious hosts that week I was there. So the biscuits, the restaurants, the courtesy, the pickup at the airport, everything was super gracious.
I'm glad you liked. Some of those restaurants no longer exist, unfortunately.
Yeah.
They did not survive the economic downfall we had recently. Okay, I think we're good to go, okay? So, my name is Alisson Daulago from IMPI. So I would like to welcome you to the Heliophysics and Space Geophysics seminars promoted by the Brazilian National Institute for Space Research, INPE. In particular, this seminar is being hosted by the Space Geophysics postgraduate program and by the Research in Heliophysics project, which is a part of the internationalization effort going on at our institute, sponsored by Kopp's funding agency. Our guest today is Dr. Greg Kopp from the Laboratory for Atmospheric and Space Physics, University of Colorado. Dr. Greg Kopp is a senior research scientist at the University of Colorado's Laboratory for Atmospheric and Space Physics. He has a background in solar physics and aerospace instrumentation. Dr. Kopp is the instrument scientist for the TIM, Total Irradiance Monitor, Spaceflight Instrument Aboard Source, TCTE, and TSIS. As the PI of the TSI radiometry facility, he helped establish the now accepted lower TSI value of 1,361 watts per square meter, which is representative of the solar minimum. Dr. Kopp visited the National Institute for Space Research, INPE, in Brazil in October 2014, when he seeded the idea of the development of a radiometer for detecting TSI. And this ended up in a doctorate thesis work at our institute with very nice results. So on behalf of INPE, I would like to thank Dr. Greg Kopp for accepting our invitation to present this seminar on this very interesting and important topic for our research activities, which is the solar irradiance. So thank you. So we asked the audience to mute their microphones during the presentation, and the audience can ask questions using the chat during the talk, the chat at Zoom. And myself and Luis Eduardo Vieira will be saving the questions during the seminar. And at the end, we will read the questions, and if needed, the person can clarify the question. For those following through YouTube, we ask you to write your question to my email. Luis, can you put back the slide so we can see my address?
Okay.
Yeah, so at the bottom of the slide, there is an address, which is alisson.dalago@impi.br, okay? So if you have any questions from YouTube, you can send us an email. So without further ado, I hand it over to you, Greg.
Great. Well, again, Allison, I thank you very much, you and Louis both, for the invitation and the opportunity to get to see everybody again, even from a little bit of a distance. But I'll talk about solar irradiances, like Allison had said. And mostly it will be total solar irradiance because I'm dealing with energetics and climate effects on the Earth. But what solar irradiance is the integrated spatial and spectral radiant output from the sun. And it provides nearly all the energy that heats the Earth's climate. So pretty much everything that's giving us the energy that we have to drive climate comes from the sun. This is a wonderful table that Andrew Kren put together as part of his thesis work. And what he's done is he's listed at the very top the solar irradiance. This is a globally averaged value that you see here is 340, which means it's 4 times lower than the 1361 watts per square meter that Allison just said that we really measure at the top of the Earth's atmosphere, just because you're going over the entire Earth's surface here. But aside from those units, if you look at the relative input of energy sources in this far right-hand column to the Earth, the sun is pretty much everything that we're getting power from. There are a lot of secondary sources of solar origin, things like reflection of the sunlight off of the full moon that then makes it to the Earth. That's down almost 5 orders of magnitude from what we're getting from the sun itself. The largest of all of these secondary sources is heat flux from the Earth's interior. This is radioactive decay and geothermal. And those are down about 4 orders of magnitude from what we get from the sun itself. So if you total up all of these things, and there are some wonderful ones in here, zodiacal irradiance, sunlight reflected off of zodiacal dust that then makes it down to the Earth. That's a whopping 0.2 of a millionth of what the sun is giving us. So there are a lot of little effects that are in here, but if you add them all up, like Andrew Kren did in his thesis, total energy from everything that's not directly radiant from the sun is 3,000 times lower than the energy we're getting from the sun. And you'll see the greenhouse gases, as much as we hear about them, they're not on this list, not anywhere, because they're not an energy source. They regulate what happens to the incoming energy, but they're not a source itself. So you might expect that since the sun's giving us all the energy, that it would really be causing climate changes. And it would if it were varying a lot. So you'd expect changes from the sun, and we do see them, but they're not huge. So in a way, when you deal with climate effects, the sun is an 800-pound gorilla. But luckily for us, it's a very placid, calm gorilla that doesn't change a whole bunch. Let's talk a little bit just to give you some appreciation for how powerful the sun is. Total energy output from the sun is 4 times 10 to the 23 kilowatts. I've just given you a number that none of us can fathom. So let's try to put that in a little bit different perspective. In 1 second, the sun puts out enough energy that it would heat the entire world for the next 1,000,000 years. So that might be a little bit easier to comprehend. While we're at it, some other fun stuff. The sun's converting 600 billion kilograms of helium, something that floats here on the Earth and used to float dirigibles for us. But every second it's converting 600 billion kilograms of hydrogen into helium, and that's what gives it the energy that it does. And that happens at the core of the sun, where the sun is so dense, it's at about 150 grams per cubic centimeter, or 13 times the density of lead. And the sun is so big, being about 100 times the diameter of the Earth, that the energy that's created there bounces around and spends about 100,000 to 1,000,000 years before it finally makes its way to the surface. And then it only takes another 8 minutes to make it out to the Earth. So then it comes sailing into the Earth, and it's the total solar irradiance coming in at the top of the atmosphere. That's the completely dominant energy source driving the Earth's climate. What happens to it next kind of gives us our energy balance. If we have an equal amount of energy going back out as we have coming in, everything is in nice equilibrium. solar energy coming in, about a half of it makes it down to the ground and gets absorbed. A third of it is either reflected by clouds or reflected off of the Earth's surface. And a little bit less than a quarter is absorbed by the atmosphere on the way in. So that's where that energy largely goes. And if you do a little back of the envelope calculation, you can look at the incoming energy, which we measure 1,361 watts per square meter at the top of the Earth's atmosphere. And you can balance that against the radiative output energy, which is emitted in the mid and the far infrared. If those two are in balance, that means the global temperature, black body temperature of the Earth would be about 280 Kelvin. So not too different from what we really have. People in climate define a forcing sensitivity, kappa, and that's given by the change in temperature caused by a change in some parameter. In this case, it could be a change in the sun's output. So that determines our sensitivity to various things. Could be the sun, could be anthropogenic forcing, greenhouse gases. But the sun itself, like I said, a little less than half of the incoming energy is absorbed by the surface, a third's reflected, and about a quarter is absorbed by the atmosphere. That absorption by the atmosphere, you can see in these graphs on the right-hand side. They're mostly in the ultraviolet. So the ultraviolet wavelengths are absorbed up in the stratosphere and troposphere, where they cause a little bit of heating. Luckily, that protects us from a lot of what would be otherwise harmful radiation. Most of what makes it down to the surface is at longer wavelengths in the visible and the near infrared. So I've just given you the total amount of energy input, but now you should also have some appreciation that it's real important to understand the spectral irradiances, that is, which wavelengths particularly are causing absorption in the atmosphere. So you need to measure both the total amount of energy to have good energy balance measurements, and you need to be measuring spectral irradiances to know how the different wavelengths from the sun are changing and affecting different parts of the Earth's atmosphere and surface. And you want to know how it varies with time. This is a movie that shows total solar irradiance in the vertical plot as a function of time for a couple-week period around what are now known as the Halloween storms from 2003, a time of very high activity. And you can see small fluctuations in the total irradiance due to the passage of sunspots across the disk. Here is a large sunspot coming onto the disk, and you'll see a huge dip. As it leaves, another one transitions on, and a third one forms. And over a matter of just a couple of days, there's a 0.34% decrease in total solar irradiance. So that's how abruptly things can change on a total energetic scale. So what are the time scales of solar variability? Over a few minutes from convection and oscillations, the sun changes about 0.01% all the time on kind of 5 to 10 minute time scales. It changes, like I just showed you, can change up to 0.3% or a little bit more over a few days. Those are short duration changes. They don't really have time to affect climate on the Earth because the Earth is sort of a big absorptive cavity that sucks in a lot of energy and doesn't respond immediately, but over longer time scales it can. Over the 11-year solar cycle, the sun changes about 0.1%, and that does have direct effects that are detectable on climate. And over longer time scales, over centuries, maybe 0.05%, maybe 0.3%, we don't know as much as we would like to because our measurements don't extend that far. Those have very direct effects on climate. One example I'll talk about in a little bit is the Maunder minimum, a time of very little activity on the sun, and Europe's little ice age in the late 1600s. Ironically, on longer time scales than centuries, we know much better how the sun varies. It varies about 0.1 billion parts per million per year on evolutionary time scales. All of these long time scale effects can directly affect the Earth's climate. So we need to know how much the sun is varying when we're trying to discern how much of climate change we have any control over. Here is the 40+ long year record of spaceborne measurements of total solar irradiance, given by over 15 different instruments from NASA and ESA, NOAA, and some others too. You're going to be included in this shortly yourselves, I hope, when you get your radiometer flying. But this is the series of measurements, and luckily you see the different offsets between these instruments. Those are calibration differences. Luckily, we've had continuity for the last 42 years, and that lets you put these together into one continual record, sort of a composite, to say what the sun is doing. And at the bottom here, I correlate the changes in total solar irradiance given by all these different instruments with numbers of sunspots. And you can see a fairly direct correlation. The sun is a little bit brighter, a little bit hotter at times of high activity indicated by high sunspot number. Now, I just showed you a minute ago that very large sunspots cause decreases in total solar irradiance, but associated with sunspots, there's a lot of brighter active regions, faculae, that overall cause an increase. So the period we just looked at in my movie is right here, if you can see my cursor, in 2003, a very abrupt, big decrease due to the passage of sunspots. But along with those sunspots are brighter, warmer regions, faculae, that overall cause an increase. And they have longer durations. So long term, it's the faculae that cause increases in the total solar irradiance at times of high activity, while sunspots, being very short duration, cause short-term decreases in total solar irradiance. Now we want to extend things back further in time. We've got a 40-year record, and that's pretty impressive. But we want to understand how the sun affects climate, and climate deals with, well, kind of at the minimum, 30 to 40 years, but really we'd like to be able to know what the sun is doing and how climate is affected on even longer time scales. So rather than wait hundreds of years to have a really good record, we try to extrapolate what the total solar irradiance has been like in the last several hundred years. And we do that. I'd already linked up what the sun is doing. We have this 40-year measurement record, and with overlap, we can put things together into a composite. And I showed you how that was kind of correlated with the sunspots that you see on the bottom of the upper right-hand plot. Then you have a good 400-year record of what sunspots are. So you can take those sunspots and via that 400-year record of sunspot number, extrapolate back in time what total solar irradiance might be. And more than just direct correlations, you can estimate other effects too. So different researchers have come up with different models for activity on the sun that could be causing long-term changes in the total solar irradiance. Now, you've heard a lot about the sunspot number a couple of weeks ago from Jose, and in a couple of days, you're going to be hearing from Ilya about other correlations, namely via isotope records that take things back further. Isotope records are indicative of solar activity, and they go back much further than our direct observations of the sunspot number, and that lets you extrapolate what total solar irradiance might be like going back 10,000 years. These are all proxies, but at least they let us extend our knowledge and our record of what we think the sun has been doing for the last 10,000 years. And of course, the knowledge is better the closer we get to the present, but at least this gives us some indication of solar variability over millennia. Now, I did link sunspots to solar variability. There also are links between sunspots and climate on the Earth. Early on, starting with the early observations in 1610, there were a lot of explanations for what sunspots were. One of my favorite is that by William Herschel. He was a brilliant physicist, But his explanation of what sunspots were wasn't completely exemplary of his brilliance. He thought they were openings in the sun's luminous atmosphere that let you see a cooler underlying surface, which he presumed to be inhabited. So he had some better work. And one of his better pieces of work was that he was the first one who published a paper that correlated solar activity with climate change. And what he'd noticed was there was a correlation between the price of wheat in London with the number of sunspots. And he attributed that to reduced rainfall when the sun had fewer spots on it. So that was the first publication that really dealt with some link between Earth's climate and solar activity. More recently, a seminal paper in 1976 by Jack Eddy really popularized the concept that the sun could be affecting the Earth's climate. What he did was he'd noticed a correlation in the late 1600s between the sun and Earth's climate. Now, if you study the sun, you know of the late 1600s as the Maunder minimum, a time when there were very few sunspots on the sun for about 70 years. I showed you the 11-year solar cycle and how variable things can be. But for these 70 years, there were very few observations of sunspots. People were looking, the sunspots simply weren't there. If you study Earth's climate, you know that same period as Europe's Little Ice Age, and the two were very nicely correlated. And Jack Eddy in 1976 published a correlation showing the sun had decreased output for that period of time, and the Earth's temperatures were a little bit colder than they were more recently. And he took things a little bit further, was even able to go back to almost 1,000 years, showing correlations between what he'd estimated via proxies of solar activity and estimates, again, via proxies of the severity of winter, but did show some good correlations that really suggested the sun was influencing climate. Now, these are periods before anthropogenic effects, human-caused effects, really caught on to things, when climate was driven much more by natural variability than it is right now. And there are a lot of causes that create climate change. Natural forcings used to be the dominant one, and they include solar variability and volcanic eruptions. Volcanoes can spew up enough aerosols to temporarily block incoming light somewhat and reduce the temperature on the Earth. There are internal oscillations, ocean atmospheric coupling modes. El Nino is a popular one that we know about. So there are internal oscillations in the Earth that affect or distribute how climate changes regionally. And there are anthropogenic causes, how we change the land use. Anthropogenic forcings such as greenhouse gases and tropospheric aerosols that are put up into the atmosphere can change how much of the incoming energy is sort of retained or kept from radiating back out and causing localized, that is, lower atmosphere heating. So there are anthropogenic effects and natural forcings, the sun being one of the natural forcings. And in order to really understand all of the effects that contribute to climate change, we need to understand and measure all of these. And what I focus on mostly is measuring the solar variability and the energy that the sun is giving to us. If I take some of these components of variability in the sun, El Nino being purple here, volcanic aerosols being short-term decreases, or increases in aerosols, decreases in temperature. Pinatubo is shown kind of here in the, I think that was 1991, as a abrupt 0.3 degree drop in temperature caused by the sulfates put up by Pinatubo's eruption. But I can take all of these different sort of components that contribute to climate change, total solar irradiance with its 11-year cycle being the green curve here, and anthropogenic effects, mostly greenhouse gases that have been increasing a lot over the last half century. All of those four together can be combined or sort of regressed to match temperature changes. These are global temperature changes at the top plot in brown, and a regression of these four components contributing to those global temperature changes in orange. So by decomposing or regressing several different effects, you can attribute how much of variability is due to each different effect of change. Now, that graph was global, but regionally, things differ as well. El Nino in the upper left tends to warm the Pacific, particularly near the tropics. The solar cycle, the 11-year solar cycle, tends to warm Europe. Europe actually seems to warm quite a bit. It gets hit hard in volcanoes. It gets hit hard by, can be hit hard at times by El Nino. Gets hit hard, real hard, by anthropogenic forcings, which you see in the lower right. So these are all ways of doing that regression that I showed you on a global scale in the last slide, but doing it piece by piece or region by region around the Earth, and figuring out regionally how much contribution you have to climate change from each of those sort of contributors to climate change or components of change. There are a couple of mechanisms by which solar forcing really work to affect the Earth's atmosphere. And they depend on the spectral irradiances that you have from the sun. So overall, the solar cycle variation of 1 watt per square meter at the top of the Earth's atmosphere causes a little bit less than 1/10 of a degree warming globally, but it can cause much higher changes regionally, indicating there's some sort of amplification or feedback mechanism. And I'll talk about a real neat feedback mechanism in a couple of minutes here. But these feedback mechanisms can amplify the effects of any forcings regionally and even globally at times. But these two main effects are what you call the bottom up and the top down effect. Bottom up is pretty much starting from the surface and getting extra heating. So starting at the surface, the light that makes it down to the surface is mostly visible in near infrared. Higher TSI, that is a little bit more energy, changes evaporation, which can change precipitation, which can change winds, which can eventually work its way around to reducing clouds and therefore allowing even more absorption of that total solar irradiance. So a little bit of an example of some positive feedback, but that would heat things from the changes in the sun's visible light hitting the surface and working its way upward, or even just directly heating the surface. Then there's top down. Ultraviolet light from the sun is absorbed in the stratosphere, and increased ultraviolet can couple to and change some circulation patterns and cause even increased heating in the upper troposphere. That then can work its way down toward the surface. So those two effects can work additively, even though they're starting off in very different places. In terms of climate modeling, I showed you that what we look for is some sort of forcing agent. It can be, in the case we're talking about mostly, it's changes in light input. But you could even consider a change in greenhouse gases here. And how much does a change in greenhouse gas cause a change in overall temperature? So for those sort of anthropogenic influences, what we've seen over the last 40 years or so is a change of a little bit more than 0.4 degrees in global heating, caused by about 1 watt per square meter of forcings attributed to greenhouse gases. And that gives you a kappa, or a climate sensitivity, of 0.4 degrees per change in watt per square meter. Now, if you look at the sun, I said, causes about a 0.1 degree change over the solar cycle. And globally average, that forcing is about 0.15 watts per square meter, because I've divided by 4 to go over the entire Earth's surface, and I've dealt with an albedo, 30% loss that we have of reflection. But that gives us a kappa for solar forcing that's about 0.7 degrees per change of 1 watt per square meter.
The effects are spectral. So especially with that top-down effect that I talked about, ultraviolet changes affect our stratosphere a lot more. Ultraviolet energy from the sun being absorbed in the stratosphere, longer wavelengths, still ultraviolet being absorbed in the troposphere. They can have some photochemistry effects that affect circulation patterns. So important not only that we be measuring changes in the sun's total energy output, the TSI, but also the changes spectrally. Now, I've shown how we've historically reconstructed what we think the sun has been doing. We also want to know, to be able to correlate them, what the Earth's climate has been. And again, there, we have pretty good temperature records going back 400 or 500 years, but not globally. We've got great records from Europe, which is where most people lived for that period of time. So we rely on other proxies to get a good global indicator of what climate has been. Ice core samples trap air, dust, and volcano dust, stratosphere, or aerosols once they precipitate out and give us an idea of what was happening when. Tree rings tell us indications of moisture, temperature that are indicators of climate. Sea surface levels, we can try to diagnose back in time via dust, ice floats, and we have various sedimentations that differ, different layers in corals, microfossils we find in different places, all of them being proxies for what climate change has been. And that lets us put together, again, better records in the more recent times on the right side, but puts together temperature changes that we think globally we had going back millions of years. This is sort of the Ice Age period back here. We live in a kind of nice warm period, Holocene up on the right side of this plot, but different meltings and global coolings or glacial coolings through this period. Other cycles that affect things prior to that, here are some periods in green of Antarctic glaciation and thawing that caused abrupt increases in temperature. So you have some indicator of what temperatures have been like. One thing that directly can affect climate via radiative forcing are changes in orbital parameters of the Earth going around the sun. Changes in precession have got time periods of 20,000 years roughly. Change in eccentricity of the orbit has got 100,000 and another 400,000 year period. Changes in tilt of the Earth are a prominent 41,000 year period. Those effects, the Milankovitch cycles, do correlate roughly with what we think the temperature has been, and that's purely through radiative forcing. Then here's a neat one that I'd promised was a feedback mechanism, and kind of an extreme one. We luckily live in an era where things are balanced. We've got polar caps, and we've got a lot of tropical lower latitude areas of the Earth where the oceans are melted. But if you were to take and start to cool things a little bit, those polar caps expand. And the bigger they get to be, the more sunlight they reflect, and the less sunlight is absorbed by the ocean, and the colder the oceans get, and therefore the more the polar caps expand. And that's a positive feedback system that can lead to runaway cases. And that initially, this was a Russian physicist who was figuring out what might happen if we had a big nuclear war and we put up enough sulfates and enough dust to really cool the Earth. And he'd said, well, if things really got bad, once you get to about half of the Earth's surface being covered by ice, you can't stop it. The ice is going to reflect so much sunlight that it's simply going to take over the entire Earth. The Earth would be completely frozen. It's what is called snowball Earth. He said, well, obviously that can't have happened or we would still be there. But actually, it's probably happened several times. There are other mechanisms that would let it warm eventually. So if the Earth, and it probably has, gets cooler, it can suddenly freeze up. Plot on the right kind of shows a time going up vertically. Ice caps expand. Once they expand enough, everything freezes real quickly. and things will sit there for a long period of time, something like 1,000,000 years. But eventually you still have things happening, putting up greenhouse gases. Volcanoes are still erupting a little bit, and maybe things have to work their way through ice, but CO2 will eventually get out and cause, via the greenhouse gas effects, warming. And once you start warming, you have an inverted positive feedback effect. You start melting the oceans, you've got a huge amount of carbon dioxide in the atmosphere, and kaboom, everything warms real quickly. As soon as you melt a little bit of the ocean, it can now absorb more sunlight, heat up a little bit faster, melt the rest of the ice. And so it can be a real unstable positive feedback system, but it's kind of a neat example of how feedback systems can really amplify any effect, such as changes in sunlight. There also, a long time ago, was kind of what's called a faint young sun paradox, time when we knew the sun early on, evolutionary-wise, was a lot dimmer than it is now, but we also know that there was water on the Earth at those times. So how did that happen? How could the sun be 30% dimmer than it is now and not have the Earth be a complete ice ball? And the reason, again, is these greenhouse gases can hold on to energy that comes in as visible energy through the atmosphere, but the radiative energy at the longer wavelengths can't transmit directly back out through the atmosphere if there are a lot of greenhouse gases in the atmosphere. So those greenhouse gases probably caused enough warming to have liquid water be available and thus life to grow on the Earth, even when the sun was a lot dimmer than it is now. So some fun history. Now let's come back to kind of the more modern record. Again, these proxies are all based on our 40-year measurement period where we've had good satellite measurements, in this case of total solar irradiance. Here are some of the earlier measurements of total solar irradiance from different instruments. And I'd said the differences between these that you see as large offsets are caused by calibration differences in the instruments. Things were going along pretty well. It started in the late 1970s, but first few instruments, you could maybe argue, oh, we didn't quite know what we were doing with those, but now we've got it all figured out. All of these subsequent instruments, they agree with each other pretty well. Here's ACRIM 1 to ACRIM 2. ACRIM 2 agreed pretty well with this Earth radiation budget sensor that went on for about 20 years in blue. Virgo was launched as part of SOHO in 1995 and started up a record in orange. Again, good agreement between these contemporary instruments. Things were looking pretty good there. ACRIM 3 launched in 1999 and beautiful agreement. So it's what I say, life was pretty good. We thought we knew what we were doing. And I've developed a rule from this. Consistency is comforting, but agreement's not accuracy. We launched the source TIM in 2003, and everybody had taken bets on exactly where it was going to lie, right in between these other existing instruments. This was supposedly a better instrument than any that had previously flown. And yet it gave a value that was a whopping 0.34% lower than all the other instruments, way outside the quoted uncertainties from all of the instruments. So life was good until 2003. And then we got the whole community together to try to understand what this cause was. So to understand the differences, fundamentally, you need to understand, these are very simple instruments actually, but they're subtle. The way they work is each of them has got an absorptive radiometer, some sort of cavity, something that absorbs, it's black, it absorbs incoming energy. So it's looking at the sun and it absorbs all the spectrum, all the light coming from the sun through a precision aperture. If you know how much light energy you're getting and you know the size of that aperture, you've got your radiance, watts, optical power per area, per square meter. So you need to know that precision aperture well. You need to be able to measure that optical power very well, which is why you guys have worked so hard to be able to do nickel phosphorus black and to be able to measure the reflectances of those cavities. Those are critical parameters in lowering uncertainties for any total solar irradiance instrument. You also then can shutter the sunlight here, so you can modulate sunlight in, get a measurement, no sunlight in, get your background measurement. Fundamentally, simplistically, this is a very conceptually simple instrument, but there are subtleties. If you want to work very accurately, say down at the 0.01% absolute accuracy level, and 0.01% is a tenth of the error bar that I show here, but you want to be able to reduce these uncertainties so you don't have offsets between instruments. So you'd really like to be able to be much smaller than this error bar, maybe down at the 0.01% or 100 part per million level. So if I say I want to build something that's accurate to 100 parts per million, right there, if I just look at how well do I need to know the size of that aperture is kind of a little less than a centimeter across. I need to know the radius of that aperture to about 1/3 the wavelength of light, or I've just blown my entire error budget on that measurement alone. So conceptually simple, but the details are critical to get correct, to drive to very low uncertainty levels. The Doppler correction, you put this instrument on orbit in a spacecraft. You can't do these measurements from the ground because, like I'd shown you, the atmosphere absorbs a lot of the incoming energy. So you put them on spacecraft. As the spacecraft's going towards the sun or away from the sun, you have a plus or minus 50 part per million shift just due to Doppler velocity. Something that you know exactly what the spacecraft is doing, how fast it's going, but you have to correct for these types of effects at this level in order to do good radiometry. So conceptually simple instruments, but the details are very subtle at times. This is a cutaway of the total irradiance monitor that first flew on source. Better design than any of the previous instruments, 4 cavities inside so you can track degradation with them. Cavities used a nickel phosphorus black, a hard metal, so they didn't degrade much on orbit. And they're mounted inside a thermally controlled instrument behind a precision aperture. You'll see the precision aperture is way up at the front of the instrument on the left side of the cutaway here, the cavity in the very back. There were several innovations that the source TIM implemented. Precision aperture at the front of the instrument is one of them. It was the first instrument to use a nickel phosphorus cavity interior, a robust metal instead of the organic paints that did degrade on prior instruments when exposed to the sun, and a phase-sensitive detection system. So everyone agreed this was a terrific design. The TIM geometry I show on the right side. Everyone had agreed this was a great design ahead of time, and yet it was wrong, everyone insisted, once it started measuring lower values than everyone else had. All the other instruments realized had a very different design. Their precision aperture sat right down next to the cavity. What that meant was they were letting in 2 to 3 times the amount of total light that they ultimately wanted to collect. And if any of that light scattered, bounced off their bevels, bounced off the different apertures higher up, they would have scatter effects that would erroneously mean they were going to read too high of a value. And that's exactly the case and the cause of the offsets that we found between the different instruments. This even affected the World Radiometric Reference, the WRR. So we realized that the TIM, being the first instrument to fly with this different design, was measuring lower than all of the others because all of the others were actually measuring erroneously high. So after some time, we launched in 2003, did a lot of figuring out of what the causes were, and in 2011, ACRIM 3 adjusted their values from what were much higher. Based on some lab measurements with an engineering prototype, they decided they had a lot of scatter in their instrument, and they adjusted their flight data to be lower. Primos was launched in 2010, released data a little over a year later. They're shown in black here. They had taken a ground-based calibration and transferred it to space. There were no prior end-to-end measurements that we could do or calibrations we could do of these instruments prior to source launching. But to deal with problems like this, we created a facility that did let us test an instrument end-to-end in vacuum at full solar power levels. And Primos was the first instrument that launched after having done that calibration on the ground. So it transferred that directly to orbit, and it validated the source TIM irradiance value of 1,361 watts per square meter. Following that, next instrument was launched in 2013, released data a little bit later. It's shown in blue, matches very well. Finally, Virgo launched in 1995, and 11 years after Source had established this lower value, realized they had a correction to make. And in October 2014, the PI lowered the value of Virgo and then was too low. And a month later, found another correction that brought everything nicely in line. This is more what I call social physics than real physics, but it is in some way how science does work. So now we have really good agreement again, and I want to remind myself to not get too complacent. Consistency that we now have again is comforting, but it doesn't necessarily mean that we have accuracy. So we still need to be questioning all the time how we make things better, whether we're really doing things correctly now. These instruments work using a phase-sensitive detection device. You keep a constant cavity temperature by regulating electrical power that you put into your cavity. So you're electrically heating it to hold it at a constant temperature as you modulate incoming sunlight. So when the sunlight is blocked, you have to put in a lot of electrical power, shown at the top of the plot on the right. When the shutter is opened, you have sunlight power that comes in, you can reduce your electrical heating, and that difference gives you a measurement electrically, which you can measure very well, of how much optical power you have coming in. So that's basically how these instruments work. We do a phase-sensitive detection method. Rather than simply take measurements at the end of a cycle, average them up and subtract them from the end of another cycle, we actually apply something similar to a Fourier transform that reduces sensitivity to high frequency noise. And that reduces our sensitivity, especially to high frequency noise, substantially from what you would get with a DC subtraction method. So there are some subtle effects like that that were implemented with the source TIM to improve the noise, the signal to noise measurements. So where are we now? We've got a 42-year-long uninterrupted record with NASA, ESA, NOAA instrument. Continues to rely on continuity and stability, have improved the accuracy substantially, like I showed you. More recently, if I blow up the current time, we've been very fortunate. We had 4 instruments overlapping for quite a while recently. Virgo, the TCTE, Source, and now TSIS-1. Virgo's been going since 1996. TCTE went up in 2013, decommissioned it about a year ago, a little less than a year ago. Source went up in 2003, was decommissioned just a couple of months ago. And TSIS-1 has sort of taken over from all of these now. Launched in late 2017 and has been providing data since early 2018 and continues to. Virgo, like I said, started in 1996, longest duration TSI measurement that we have. Sitting out at L1, it's not occulted like all the other instruments are by low Earth orbit, where it's blocked by the Earth every 90 minutes. So straightforward, nice, unaliased power spectra that you can create from the Virgo data. Unfortunately, the PI passed away a couple of years ago, no, just a year ago, but hadn't updated the data in a while. So we don't have any new data from Virgo since May of 2018. The instrument's still operating, it's still taking measurements, but there have been no data releases for the last 2 years. But hopefully will be in the future. Source has been going for 17 years, better intrinsic stability because of the nickel phosphorus than any prior instrument. And it's provided one of the longest duration irradiance records. It has established the lower value, 1,361 watts per square meter, that's now accepted as the correct measurement of the TSI. It was also the first instrument to measure in total solar radiance a flare. Flares are big events energetically, but not big compared to the total amount of energy coming from the sun all the time. Where you see them easily is in the ultraviolet and X-rays, where the sun doesn't put out much energy normally. But in TSI, because there's so much energy at all wavelengths from the entire surface of the sun coming all the time, you don't see flares very much in TSI. We did get to see one of the largest solar flares ever recorded and could measure it in TSI, and it's the spike shown in blue right here. The neat thing about measuring a flare in total solar radiance, unlike just in the ultraviolet or X-rays, is it lets you integrate all the radiant power from that flare. So you know how much total power really is in the flare from this measurement. So SOURCE provided that first measurement. We also observed a couple of transits, 2 transits of Venus and 4 of Mercury. Venus is a bigger planet and closer to the Earth. It's shown on the right side here, and it causes a pretty abrupt decrease in energy output from the sun, like a sunspot, like a medium-sized sunspot as it transits across the disk of the Earth, or of the sun. Mercury is much smaller. It's shown on the left-hand side. The measurements, orange from TSIS, red from SOURCE. The sun is moving around, like I said, on minute time scales at about the 100 part per million level. So this is not noise in these measurements. That's real solar variability. And on top of that, you have suns changing at the 100 part per million level all the time. You have a 40 part per million decrease due to the passage of this teeny little teeny little planet moving across the sun. Very hard to see. So we've had a couple of 4 opportunities to try to see these. We've observed every one of them. None of them are things that you would look at and say, there's a detection of Mercury. Nothing that's statistically significant. Neat example, though, of something that exosolar planet searches are up against as they try to find small planets against sun-like variability stars in the background. TCTE was intended to bridge a potential gap between SOURCE and the next instrument, the TSIS-1. So it launched, it provided good measurement redundancy, and luckily SOURCE kept going long enough to be able to overlap directly with TSIS-1. But in the time it was up there, TCTE did also contribute to another observation, not detection, of a Mercury transit. And this instrument was just turned off a little less than a year ago. TSIS-1 went up a couple of years ago and has been producing data since early 2018. It's the most accurate on an absolute scale of any of the instruments that have ever flown, being down at the 150 part per million level, and shows very good agreement with all of the other instruments that are concurrent. That's the only instrument that's still providing data right now. These are all the different missions that have contributed to the data record. And first, I want to call your attention to a time here in 2013 when we were really fortunate. We had Primos going with 2 instruments on it. We had SOURCE-TIM going. We had ACRIM-3 going. We had Virgo going. We had 5 instruments taking measurements simultaneously. Let me show you what can happen to 5 instruments in a short period of time. SOURCE, at the end of July in 2013, had battery issues and quit taking data. We didn't know at the time we were going to find a way 7 months later to get it working again. We luckily did. But at that time, we'd figured that was the end of the mission, the end of those measurements. Like I said, we had 5 instruments going when we started this. ACRIM-3 had been going since 1999, but on September 17th of that year, its transmitter quit communicating with the Earth and we lost the ACRIM-3. Primos was going and was turned off, scheduled for decommission, and it quit in February of 2014. SOVA-P, same mission, quit a couple of weeks later, was turned off. almost bridged this gap where we started source up again, but not quite. And we really didn't know that source was going to function properly when turned back on, when we found a way of turning it back on. TCTE, this gap filler, wasn't ready for launch at the time that source quit, so it didn't start until much later. The only instrument of these 5 that had been working that bridged this gap between source was Virgo. So that's how quickly you can go from having good, robust measurements to being very concerned that you're going to maintain any continuity in this data record. So now we're in a period where we've just turned off a couple of instruments. The only one producing data is the TSIS-1 right now. Virgo is still taking data, but not producing it, not releasing anything. I'd be very worried, except the future looks promising. We're expecting updates from Virgo. NORSAT Clara has been up for a couple of years, but hasn't released any data yet. There's possibility we'll be getting some data from that eventually from the PMOD group. The PMOD group is also going to be launching DARA coming up this next year. Here at LASP, we're working on a compact CubeSat TIM using carbon nanotubes instead of nickel phosphorus as the absorptive black. But it'll be a 6U CubeSat size instrument that should be ready for launch next year. And TSIS-2 has a TIM on it. It's a rebuild of the TSIS-1 TIM. And we're building that now for a 2023 launch. So the future does look promising. The TSI record currently looks like this. And it's been because of overlap in the different instruments that we can put together a composite, such as I show here. What you'd really like as a climate user is to have somebody put together a composite for you. Well, you're fortunate. There are 3 prominent composites. Maybe you're unfortunate. Now, which one do you choose? Each of these is put together by a different PI, and you can guess which instrument they favored when they made their composite. So there are different composites created by different individuals with their own kind of biased selection of which instruments they used when. As a function of time, shown here are the different instruments chosen at different times. There are discontinuities at the boundary when you move from one instrument to another. There are controversial corrections that a PI may have applied to somebody else's data even that can affect the composite they build. The normalizations are incorrect. That is, all 3 of these can't be on the right scale. Which one's right? And none of them really have uncertainties associated with them. So we've been working on what I call a community consensus TSI composite. And this is something that's supported by the TSI community, not by an individual, but by a group of people working in the TSI measurement area. We use all available instrument data instead of one instrument at a time. We do weightings to smoothly fill gaps. We use a kind of unbiased statistical approach that's a lot less biased than an individual PI. Normalize things to the most accurate instrument, and we do have time-dependent uncertainties. So this is a new composite that we're aiming to make into a new product in the future so that climate users have one composite that they can use that's got the consensus of the TSI community behind them. Now, I did also show historical reconstructions linked to sunspots, and you're going to hear more about historical reconstructions in a couple of days from Ilya. So I will say that the sunspot record, like you also heard a couple of weeks ago from Jose, has been changed recently. We build historical reconstructions based on the sunspot number. Sunspot number changed about 5 years ago due to better processing, better methodologies, better historical data. How does that now affect our reconstructions? We've got a team working on that as well. What we do is we take a composite, link it to the 30-year record or 40-year record of overlap with sunspots, and like I showed you before, take that sunspot record and then go back in time to historical TSI reconstructions. In the lower left here has been what we have been working with, but new estimates of what the sunspot number are mean that we've got to reconstruct a lot of those models. So that is something that we're working on now. I've done some preliminary work on that using data from both the NRL group and the Max Planck Institute für Sonnensystemforschung group, the Satire group, with their models. So 2 different models of TSI and their sensitivities to sunspots, and therefore the resulting effects that changes in sunspot number would have on what we think TSI has been doing for the last 400 years. So that's kind of where we're going with these new measurements, and we've made some progress on that fairly recently. But overall, the TSI measurements, I want to summarize, they're the most stable solar irradiance measurements that we have. They've got the stability levels at the instrument level to be able to start to see climate relevant solar variability on multi-decadal timescales. They so far are providing a 42-year record of solar irradiances, gives us the entire radiative input to the Earth's climate system. And there is the importance also of the spectral solar irradiances, which tell us where that energy is going in the Earth's climate system so that we can figure out how the climate system is responding to variability from the sun. So let me end there. It's a 1-slide summary of everything that I talked about, the solar variability and how it affects climate science here on Earth. And happy to take any questions anyone has. Thanks.
Oh, thank you very much, Greg. It was great. So we are applauding you virtually.
Thank you.
Yeah, we have a few questions. We'll read them, and if the author of the question wants to clarify, he can speak. So first one is from Romaric Gravet. He says, hello, Greg. Have you some news about compact SIM?
Oh, I do. Hi, Romaric. No, it's been working. It was launched about 2 years ago. So compact SIM is, for everyone else, is an instrument that measures spectral solar irradiances. Along with the TIM on source and on TSIS-1, we've flown what's called the spectral irradiance monitor, something that works from about 350 nanometers up to 2300 nanometers in wavelength, but does so with spectral discrimination so that it can tell which parts of the solar spectrum are varying by how much. So we've had 2 large SIMs that have flown. What the CSIM is a compact spectral irradiance monitor. It's a 6U CubeSat that, like I said, we launched a couple of years ago. We control out of LASP. Eric Richard is the PI in charge of it. And it has achieved very good noise levels compared to the prior SIMs. It really is kind of intended as a first demonstration instrument that you could make something compact and cheaper, but it's been much more successful than merely being a demonstration. It's shown real good overlap with the SIM on both source and even better with the improved SIM that's flying on TSIS-1. So yes, flying, operating nicely, and providing good data. Thanks, Romer.
Okay, so next question is from Franciele Carleso, it's our postdoc at INPE. She asks, can gaps of days to months in TSI measurements influence the understanding of the solar variability over long time scales?
Neat question, Franciele, and glad you're on there as a postdoc too. Gaps of a few days, probably not. These instruments on long-term timescales, gaps of a few days are neat, or kind of timescales of a few days are neat if you're watching changes in the sun's output. That is, how does the irradiance respond to changes in solar activity, to a sunspot that's created? Those are things where you want to build up models where you need short, that is daily or even faster timescales. You see a sunspot evolve, you see the corresponding change in TSI, and you want to create a model that tells you for a certain type of activity, this is how solar variability has changed. But for climate change, a gap of a few days doesn't make much difference. And the reason is the instruments are very stable. You can keep them, they're thermally stabilized, they don't degrade very quickly. So they're very good at maintaining long-term stability. And for climate, that's much more what you do care about. So having an instrument disappear for a couple of days isn't a big deal, as long as it's thermally recovered. That is, you thermally stabilize it when it comes back on. So in terms of climate, as long as it's a stable, thermally stabilized instrument, not a big deal to lose a couple of days of data consecutively. And in the case of source, we even lost data for 7 months. And the instrument's stable enough that to within 50 parts per million or so, I can't discern any change between the before and the after period across that 7-month time scale. It would be real reassuring to have something that really did match across, very solidly match the beginning and the end of those data sets. But that's over a much longer time scale. And even there, the thermally stabilized instruments are pretty good, even if they're off for a while, but certainly on the couple of day time scale. For climate, it doesn't matter. For understanding the solar physics behind the variability, it is where you want the shorter time scales. Thanks, Rinsel.
So next question from Jean Carlos Santos, who is a faculty member at the University of the South of Brazil. Jean says, 11-year variations in TSI are caused mainly by variations in the photosphere, faculae, if I understood correctly. What about faster variations? Are they all associated to photospheric physics too?
They are, and you're correct. It is the photosphere. That's where the visible and near infrared are emitted, and then the atmosphere is, it's got very little opacity above there. There are spectral lines where it does absorb, but for the most part, the energy is coming directly from the photosphere. And the high frequency changes are also associated with the photosphere. They're the superposition of 5-minute oscillations and convection bubbling on the surface of the sun that cause short-term changes, that is minute or several minute timescales, where we can see convection, granulation, and 5-minute oscillations. The higher up energy, you see beautiful pictures, say, of the corona in X-rays. But the corona, those higher, very high layers in the atmosphere, the corona is a 1 part per billion effect of the total energy from the sun. So pretty much all of the sun's energy, except for maybe that 1 part per million coming from the corona, pretty much all the energy is coming from the photosphere, and all of the high frequency short period changes are associated with convection and granulation are coming directly from the photosphere, and nothing really from high up, simply because the energy isn't there to start with. Even the background energy, say in the corona, isn't that significant compared to what the sun is producing from the photosphere all the time. That's true, at least in TSI. Now, in spectral irradiances at some of the shorter wavelengths, you can say that it's got to be coming from higher up. And especially if you get down to the extreme X-ray, those are all emitted high up in the atmosphere. But on a net energetic scale, they're down well below a part per million of what the sun is doing in the total irradiance. Thanks, Juan.
So next question is from Dr. Panda from India. I don't know if you are able to answer this, because he says we entered the solar cycle 25, and he asks whether are there any problems to download data from SOHO satellite. I'm not sure you're the one to answer this.
Oh, okay. I can at least answer for the SOHO Virgo, and that is that in terms of, SOHO is still producing data, but at least for Virgo, the instrument that's measuring total irradiance, the data are still being downlinked, but they're not being processed, analyzed, and released right now. So the data that we currently have from Virgo ended 2 years ago. Newer data are available, and there is a new group working on them in Davos. but they haven't released any data updates in the last 2 years. So yes, we are heading into the next solar cycle. We may have even gone through solar minimum, something that you don't really know until you see you're definitively coming out of it. But we have other instruments that are producing data now that can show different effects of going through solar minimum and perhaps coming out of it, the TSIS-1 being one of them. But while Virgo is still producing data and the data are being downlinked and collected, the group to release them has not released them in the last 2 years, I'm afraid. I'm hopeful that it comes along soon.
Okay, so next question from our colleague from INPE, Claudia Medeiros. She's asking whether you try to compare the irradiance measurements by solar panels on board other satellites to infer the TSI, to fill the gaps when you don't have measurements from the radiometers.
Yeah, these instruments, the real TSI instruments are incredibly stable, incredibly accurate. Thermal variations can cause huge changes in sensitivity of an instrument. Solar panels, they're not really designed to get anywhere near the sensitivity and definitely not the accuracy that you need to be able to see small changes. We're looking for changes that are about 100 parts per million. And if you're going to do that, I'd shown that example of an aperture. If you mismeasure the diameter of an aperture by 1/3 the wavelength of light, you've just shot your entire 100 part per million error budget. So now think of that aperture getting exposed to the sun and then cooled. It's going to thermally expand and thermally contract. It'll be a different size. That alone is going to be a bigger effect just from thermal influences than the sun itself is causing, a bigger effect than you're trying to measure. Now on the instrument itself, you measure the temperature of that aperture real accurately so you can make that correction. But if you want to use something like a solar panel that's designed to produce power, they're designed to absorb light. They're dark, they heat up a huge amount. They can get extremely hot in orbit where there's no air around them to be cooling them. Their thermal variations are huge. Instead of being at the 1/10 of a degree like they are on this instrument, they're tens of degrees. And the sensitivity of the response of the solar panels is huge. So not something that you can really accurately count on as a measurement of the sun. You'd have a really good indicator of the temperature of that solar panel as it's exposed to the sun and not, but you're not going to get a real good measurement of what the sun is doing, I'm afraid, with anything like that. So these are subtle instruments and subtle measurements that you have to make. 100 parts per million is easy to say, very difficult to actually do.
Okay, so we have a next question from doctorate student at INPE from the Applied Computing course, Amita Murali Krishna. She is asking, could you please tell me more about the time-dependent uncertainties you've mentioned in slides 56 and 57?
Ah, yes. Let's see. Great. So this is something that's really important and something that's been neglected in all the previous composites. And the reason this is dangerous is people will take a composite as the ground truth without realizing that there are uncertainties associated with different eras that went into producing a composite. So what I've shown here in red are the daily measurements produced by our composite. Black is sort of a smoothing through them that shows the solar cycle, and in faint blue in the background are the uncertainties as a function of time. Those uncertainties depend on how much we trust each of the instruments, how high their noise levels were, and how many instruments we had contributing to the data record at that time. So if you've got 3 instruments and they agree pretty well, you can reduce your uncertainties as a function of time, or if you have one instrument that's shown very good noise characteristics, it will have lower uncertainties. So on the bottom here, I've shown the uncertainties associated with different time eras of this composite that we've put together. And the more modern instruments are better calibrated than some of the older ones are, so lower uncertainties there. They also have lower noise, some of that being due to the phase-sensitive detection. And that's why the more modern measurements have got lower uncertainties associated with them than the prior ones. There are different periods, this here being a period around 1990, when one of the acronyms had quit working, and all of a sudden we were down to only 2 other instruments and they had higher noise. So that was a period where we had better, lower uncertainties initially, lost one of the instruments contributing to the record. The uncertainties increased briefly, and then when we did start to get another instrument, they decreased again. So that's why there are some time variability. This isn't a monotonic trend in uncertainties. It does vary with instruments being lost, being launched, and it does depend on the intrinsic instrument stabilities and noise levels, with the newer ones being much better than the old ones. What it does mean is that if you want to take a kind of recent measurement and compare it with something, say, within the last 10 years, you can do so with pretty low uncertainties. But if you want to take a measurement from around 2000 and compare it with something 10 years prior, you've got a much bigger change in uncertainties during that time era. So that's why we thought it was important to have time-dependent uncertainties. Is if you're looking for solar variability between any 2 times on here, you need to know how reliable the data were at those 2 times. And that's what we've tried to produce along with this new composite. But a really important thing to be able to have users understand, instead of simply giving them one time series and have them not know which parts of it are more reliable than others. Thanks. Glad you asked that question.
So next question is from Luis Eduardo Vieira. He asks, could you compare the TSI variability to solar luminosity variability?
Oh, they're almost directly related, and that is that the solar luminosity is determined by the temperature of the star. Solar luminosity itself actually varies, but they're essentially the same things, and you can relate them through the temperature of the star. That's actually even been done, but in a circular way. I think it was 2015 that the IAU adopted the 1361 watts per square meter value for TSI to determine what the temperature of the sun is. And from that, they determine the luminosity. So they are kind of directly linked, but it's kind of a circular link going through the bolometric temperature of the sun. That value, I think, came out at 5,778 degrees Kelvin or something. But it is a direct but somewhat circular method that the 2 are linked, the TSI being more accurate than a direct luminosity measurement.
So next
question, Louise.
Okay, yeah, let's move on to the next question from our doctorate student, Felipe Oliveira. He asks, can high solar energetic particles change the irradiance measurements, whether by effects of radiation emission or because of their interaction with the instrument's walls or something like that?
Yeah. Solar energetic particles energetically don't have much energy, so they don't really have a big change in total solar irradiance. On things like photosensors or silicon detectors, they can cause noise, they can mess up your electronics. These devices are bolometers. They're conceptually incredibly simple. The cavities that I showed are black absorptive cavities that absorb all the incoming energy. And by all, I really mean they span the entire spectrum. Once you get down to short enough wavelengths where you're able to penetrate straight through about 4 millimeters of solid silver, things that are more energetic than that, we wouldn't be able to detect. But that gets us down pretty far into the X-rays and very high energy particles that would not be stopped by these bolometers. So for the most part, we would be able to detect them, but there's very little energy in them. So they wouldn't have an effect on the signal via direct detection. Now they can mess up our electronics, and that could cause a reset or something of the controlling electronics. But being as these are thermally stabilized bolometers, you might have to restart your electronics, but the thermally stabilized detector, the bolometer, wouldn't be affected. Another way they can affect things is with long-term degradation. The high energy particles could be changing the characteristics of the black nickel phosphorus inside the cavities, or on prior instruments which use black paints, that they can crack and degrade that paint real easily. So almost all the instruments that fly use a redundant cavity system. They use one cavity as their primary measurement cavity, and intermittently they will simultaneously use a secondary cavity. So the idea is that one of the cavities is exposed to the sun all the time, and it may degrade somewhat. Then the secondary cavity, which is more pristine, hasn't had a chance to degrade the same way due to solar exposure. So by comparing them at the beginning of the mission, and ideally they would measure the same exact value at the beginning of the mission, if over time you see the primary one changing slightly in efficiency, you can correct for it. You can track its degradation and apply a correction to it on the ground. And that's an approach that's used by all the instruments, but that's a kind of direct way where long-term degradation can be caused by SEPs on the instrument. So it's either via changes to the electronics or long-term degradation that SEPs could directly be affecting the instrument. Now, in terms of climate, SEPs can have a bigger effect because of what they can do to the upper layers of the Earth's atmosphere. So they can more directly affect climate than they can easily affect the TSI measurements. So yeah, long-winded answer to what's a neat question, but one I've wondered about a lot as well. Thanks.
Sorry, just a second. Yeah. So next question is from Somnia Krishnamurti, probably from India. The question is, can G mode contribute to high frequency variability?
Ooh, I suppose the answer is yes, of course they could. It's just a matter of how much it would be. And being as they're so incredibly hard to measure, that they would be contributing, but probably at a fraction of a part per million, if even that, in terms of temperature changes in the sun globally. So yeah, I'd expect just from physics that they should, but it would be at a completely undetectable level compared to the entire energy output from the sun, just because that entire energy output is so huge to start with and the changes from G modes so small. So physics, yes, the answer has to be yes, but yeah, I don't know how small it would be. Certainly not detectable with what we have now.
The next question from Augustinus Gudawan. How much CME occurrence can affect the TSI measurements?
Not at all. At least for a detection of the energy, just because the energy isn't there. The flare that I showed was a X17 flare, and it did have a CME with it. But that X17 flare at the time, that was the third largest flare that had ever been recorded. A week later, it became the fourth largest flare because there was another flare that was even bigger, in X26, I think. But that X17, centered on the disk, aimed right at the Earth, caused a 270 part per million increase in TSI. And that's the integrated energy of everything released from that flare, all the magnetic energy that gets converted to radiant heat, everything. It's only 270 parts per million. So the CME that also has to be released, or could be released from that same magnetic topology, is presumably a part of that energy initially released from the sun. So it could be a small fraction perhaps, or the energy that got the CME started could be a fraction of that 270 parts per million from the flare, from the magnetic topology changing and the radiant output. Now the CME itself, being a fraction of that total energy, comes out and expands, and very little of it's going to hit the instrument in the first place. But it just doesn't have the energetics to cause a big change. I know there are these things in solar physics that we really enjoy. Flares are fantastic. They're brilliant when you look at them in the ultraviolet and the X-ray. CMEs are amazing when you've blocked out all the energy from the sun. But like I said, the corona itself, the total corona, is a part per million of the TSI as a whole. And a change in the corona, maybe you double or triple that part per million. It's still minuscule compared to the TSI. So just to have some appreciation for how much power is coming from the sun, there just isn't the energetics in flares or CMEs or any other short-term activity that there is in the total integrated energy from the sun. So really not detectable, aside from what I had just talked about. The high energy particles from the CME could affect the electronics on the instrument, but certainly wouldn't be a direct measurement level. Yeah, another fun to think about question, but insignificant compared to the TSI. Thanks.
So next question from Fabricio Carvalho. He's from our city here in São José. He works on oceanography, and he asks, what period between ages of heating and freezing do you expect we are going through? And what about man's action on climate? He follows a lot of ice melting and freezing and temperatures in countries and so on. So that's his question.
We're in terms of the sun, we think we're in what's kind of called a modern maximum, a time when the sun has been fairly active. The 3 cycles prior to the last one were fairly high amplitude solar cycles. So a time when we think the sun has been pretty active and maybe getting back to what's more normal. Oh, it's kind of funny. A solar physicist's career is about 3 solar cycles. So we've had 3 good active solar cycles, and people think, oh, this is normal because this is their career length. But more realistically, if you look at the long-term record, the more recent period has been a little more active than the sun usually is. So maybe what you'd call a modern maximum. In terms of climate, we are heading into more warming, global warming that everyone knows about. If I look at some of the reconstructions, I'll see if I can find something kind of quickly. Let's see. Yeah, Jack Eddy did a little bit of this, but it was more this here. These natural components, how much the sun or volcanoes are affecting warming right now, they're less than 15% of the warming that we've had over the last 100 or more years. So most of the warming that we're seeing now climate-wise is from anthropogenic forcing. It's certainly important to measure the other effects, the ones that you can't control, in order to be able to discriminate how much sensitivity we have to which different effects. if you look at the TSI dropping at times, it can cause a decrease in global warming that's about as large as the increase we would get from anthropogenic forcing. But it's only going to last for a couple of years, and then it's going to reverse. So overall, on decadal or multi-decadal timescales, the anthropogenic forcing is far outweighing the natural effects that we have. So even if the sun has been kind of at high activity levels, and maybe it's dropping a little bit now, it's still dominated by the anthropogenic forcing that we've had going on for the last century or so. So I expect we're going to be seeing more warming. We've hit several records globally the last few decades. We've had lowest levels of sea ice extent, like you probably know, in the last few years. So globally, we're seeing the signs of warming. Unless we do something very drastic, these anthropogenic effects, which far outweigh the natural influences, are going to be driving our climate more than any of the natural effects are. So I'm sorry to give you that answer. It's not the one we would like, but it's the most realistic answer. Thanks.
So next question is from Patrick Bartholow. He's from California, and he mentions he has 50 years of HF radio indirect observations experience from California mostly. And he wrote a very long message. I will send it to you, but I will summarize that he is also flying high altitude balloons, and he's asking whether you have some new kinds of sensors and whether he could be of your help to make any measurements that would help this kind of studies.
Let's see, we can't directly measure TSI from the atmosphere for two reasons. One is there's always a little bit of absorption. I've flown high altitude balloons up to about 37 kilometers. And even there's a bit of absorption in the shorter wavelengths that keep you from getting accurate measurements of the irradiance. But more importantly, you're working in a regime kind of at the limits of what you can fly to, where you're not in a completely radiative dominated region and you're not in a convection or conduction region. There's still enough air pressure to not let you be in a true vacuum. And being as these are thermal instruments, that air conduction is a big effect on the instrument itself. They're really designed to have radiative coupling or mechanical coupling, but not be susceptible to air. And even at those high altitudes, at least these types of instruments would have too much thermal sensitivity from the kind of unknown air environment. So even high altitudes isn't complete vacuum, and that would be the biggest limiter on the instrument itself. Smaller one probably being just that there is still enough absorption in the atmosphere that you wouldn't be getting the full spectrum into the instrument in the first place. But the thermal one is the one that I would worry about even more. Yeah, neat idea, nice offer, and I'll think about it more, of course, but that's kind of my initial thought. Thanks.
Okay, so next question from Franciele Carleso again. She's asking, what is the main challenge you highlight for obtaining stable and accurate measurements by the compact total irradiance monitor? If you could share with us, what are the next steps of new generation of radiometers?
Yeah. The next steps, we went from organic black paints to nickel phosphorus that you're real familiar with. And that was a wonderful improvement in terms of stability. And to give you an idea of how nice an improvement that was, let's see if I can find my slide that dealt with the instrument itself. And yeah, so these black cavities are nickel phosphorus. The degradation I'm showing on the upper right-hand plot This is from 15 years or so of on-orbit observations. And that primary cavity being exposed to the sun most of the time with the nickel phosphorus interiors degraded by about 200 parts per million. If I took an organic paint, Virgo over that same period of time degraded by 4,000 parts per million. So 20 times higher degradation from paint to the nickel phosphorus. So that was one whopping huge step. Now the next steps are, let's get something even more robust than nickel phosphorus. Let's get something that transmits better thermally or conducts better thermally than the silver that we used here. That those are material-wise the two next big steps that we're actually using in the CTIM. We're using a silicon that conducts better than the silver that we have here with a diamond substrate on it. And diamond conducts incredibly well. And we're using carbon nanotubes instead of the nickel phosphorus. Carbon nanotubes give about a 10 times better absorptivity than we have with the nickel phosphorus, and should be more stable. So we don't have on-orbit proof of that yet, but just from ground tests, they're more stable and they're blacker than the nickel phosphorus is. They're much more uniform, they're easier to produce. So in terms of materials, the materials changes are going to the carbon nanotubes and higher conducting, faster conducting substrates, things like diamond and silicon. In terms of the measurement itself, I actually have some concerns. I think at the materials level, the radiometer is going to be better with those new materials. And if I were to put those materials inside this same instrument, it would be an improved instrument all around. It would have the thermal stability that I get from this huge mass and the better conductivity and absorptivity that those new materials would provide. The danger is if you make it small now, and instead of being this nice thermally controllable large instrument that I show here, the danger I see is flying, the bigger concern I see is flying it in a small CubeSat where you don't have the ability and the power to be able to thermally stabilize things as well. So while there are some nice improvements in the materials, the downside of a CubeSat is it has worse thermal stability. So the brute force approach, of course, is to take the best of each of them, take the carbon nanotubes, diamond type substrates, and put them in a big massive instrument like we have with the full TIM here and fly it on a big huge spacecraft. So that would be kind of the best all-round version, the Mercedes or the Cadillac version of the instrument. The advantage that the CubeSats have is that they're a lot cheaper. And if you're worried about continuity in the record, maybe you want things that you can launch quickly, that you can get ready. You can build a whole bunch of these and have 5 of them flying at the same time instead of putting all your eggs, all your expensive dollars into one basket and perhaps having a mishap with that spacecraft. So the CubeSats, if you do enough of them, they may individually have thermal issues, but maybe you can get them up quicker, or maybe you can keep more of them on orbit. So maybe they have advantages in terms of measurement continuity. But the short answer is the best thing would be to combine those new materials with a whopping big instrument that's thermally stable. Thanks, yeah, neat question. Thanks, Francel.
Next question from Danny Oliveira from Goddard Space Flight Center. He is asking, why is there a big dip in Virgo TSI data right before 2004? Is that related to the Halloween storms, and how?
Let's see, in the Virgo data, where was that? Oh, yes, right back here. That was the late 90s, and that was what they call the SOHO vacation. SOHO, designed to look at the sun all the time. There was a software kind of operations issue that mispointed the spacecraft by a ground caused or a operator caused error, mispointed the spacecraft 90 degrees, and it lost power on its solar arrays. So for a few months, a couple of months, they were off for a little over 3 months. They really thought they'd lost their flagship mission. Couldn't communicate with it, had no data from it, didn't know what it was doing. Luckily, it had mispointed from the sun by 90 degrees, but held that position. And when it came around in its orbit, going around the sun, sitting out at L1, eventually those solar panels started to get sunlight on them again, and they recovered the entire spacecraft, let alone just this one instrument. But that, what's funnily called the vacation, because it did come back, is the cause of that gap that you see there in the late 90s.
So I think he was referring to the 2004 dip, and it should be related to the Halloween sunspots.
Oh,
that one. I think that one was he referring to.
Okay. Is it this dip right here?
Yes, I think so.
Okay.
He's not at the Zoom. I think he's sending the question to Luis, right, Luis?
Okay. No, that dip right there is that Halloween sunspot, the one that I showed in the movie, caused the 0.34% decrease in TSI. So it wasn't a data gap. It actually is a measurement of the sun, and the sun for a couple of days was 0.3% lower than it normally is. So you see that dip here in the Virgo data. You see it right here in the source data. It's in all the instruments because it truly is solar. Oh, I'm sorry, I misspoke on source. In source, it's back here. But it is in the measurements from all the instruments that we're observing because it is caused by the sun.
Okay. So I will ask Giancarlo Santos' question, even though he says you answered, because it's important. He says, if someone asks me if the sun is responsible for climate change lately, what should I answer? By your talk, I understand it has a minimum effect.
Yeah, the sun's responsible for a very small amount of climate change. And by very small amount, less than 10%. So that's kind of the short answer, is that the sun is contributing, but it's not by any means the dominant cause. It's well less than 10% or so. Yeah, important question. I'm glad you asked it again, Allison.
Next question from Emmanuel Vieira. He's a PhD candidate in engineering at the south of Brazil, if I'm not mistaken. And he's asking, is the excess thermal energy absorbed by the radiometer sensor, if this energy can be reused in the subsystems of the instrument? I don't know. He works on the solar energy.
Yeah, in a way, it is. Let's see. I need to get up. So what we do, and it seemed I had an even better slide that would show this. There we go. So in a way it is. What we do is we put in electrical power to heat the cavities, to keep them at a constant temperature. When there's no sunlight coming in, we have to put in a lot of electrical power to keep them at a certain temperature. When we have sunlight coming into the radiometer, we reduce that electrical power, and the cavity stays at the same temperature because now it's mostly heated by that incoming energy. So by using the sunlight to heat the cavity, we reduce the electrical power that we need to keep that same temperature. So in that sense, yeah, we are already benefiting from the radiometer absorbing radiant power and us getting to benefit by not applying as much electrical power to the cavity. But in comparison to the entire spacecraft, well, even there, the entire spacecraft is all powered by solar to start with. So the energy that we're getting is already solar power that's been converted to electrical power that's used. So overall, the entire spacecraft being run by solar panels, we are using the sun's energy. But on the smaller scale of the radiometer, even there, when we have sunlight coming into that radiometer, we do get to reduce the electrical power that we're applying. But even that electrical power is very clean energy, having come from the sun and solar panels in the first place.
Okay, so I will do read the last question from Krishnamurti again, asking, is there any chance to observe the impact of irradiance variability on other planets of the solar system?
Yeah, there is. And because the irradiance depends on the portion of the disk that you see, I showed the effects that a sunspot would have on irradiance. Well, when that sunspot's around the backside of the sun, it doesn't affect us here at the Earth. But if Mars were on the other side of the sun, it would be affecting Mars at that point. So you can, and it is important if you want to understand how other planets are responding, it is important to measure the irradiance at that planet. We have a mission, the MAVEN mission that's at Mars, where they're trying to understand atmospheric loss from the planet Mars. And one of the instruments they're flying is an ultraviolet irradiance sensor, because the ultraviolet would ionize some of the atmosphere in Mars and cause atmospheric loss. So it is important to be able to do measurements at the planet that you're interested in of how much solar energy or solar variability you're having that could be affecting that planet, whether it's across the entire spectrum or whether it's atmospheric loss caused by ultraviolet changes. So it is important. You can't measure it in one place and know it uniformly around the sun. Another kind of extrapolation to that question is most of the activity that we see on the sun is from the lower latitudes, equatorial or 30, 35 degrees in latitude of the sun. And that causes most of the solar variability, is the magnetic activity at those latitudes. The poles, in terms of sunspots, never see sunspots. They've got coronal holes, but those are minuscule in terms of total energetics. Would be interesting to even get out of the ecliptic and know how the sun's irradiance varies as a function of latitude that you're observing. So neat question. Short answer being, for planetary studies, yes, it is important to measure at the planet. For solar, it would be neat to measure out of the ecliptic even. Thanks, Krishna.
Yeah, I'll read one last question and then I'll stop. Is from Malvi, asking, is there any correlation between sunspots and solar activity and rainfall?
Rainfall is very localized, and so in terms of short term, that is sunspot today on the sun in rainfall, no, you wouldn't be able to link them. But there are solar or cycle effects, seasonal, 11-year cycle effects, where you can, in some places, see changes in rainfall in fairly large regions. So on solar cycle timescales, there are some correlations, not much in the way really of understanding the causes, but like Herschel published in 1801, he correlated sunspots over solar cycles with rainfall, with wheat growth, and with the price of wheat. So there are long-term changes, solar cycle changes or links between the solar cycle sunspots and rainfall in some areas, yeah, but not short-term, not day-to-day or season to season, only over these longer time scales like 11-year solar cycles. Neat. Thanks.
Okay, so I would like to thank all the audience for such interesting questions, but most of all, I would like to thank Dr. Greg Kopp for such an interesting talk and such a nice topic to share with this plural audience, I would say. And on behalf of the Spatial Physics postgraduate program at INPE in Brazil, and also on behalf of the Research in Heliophysics project, which is our internationalization project in the postgraduate at INPE, I would like to thank Dr. Greg Kopp for this seminar.
Oh, thank you very much, Allison and Lewis, for getting this set up, and very flattered to have so many of you attending today. Enjoy.
Yeah, thank you very much. Thanks to all the attendants also.
Cheerio, everyone.
Thank you, Greg. I hope next time you come in person.
That would be great.
We can meet in person. It will be great. Yeah. Let's hope the next normal life will still allow this old-fashioned thing of getting together in person, face to face.
It's wonderful to see you guys again, but it's always more wonderful to really get to see you in person.
Yeah. Yeah. Okay.
I'm glad we could at least do this.
Yeah, thanks. It was great. The connection was good. So I think my audio signal was without interruptions. So it was really great. Thank you very much. Yeah. This presentation is recorded and it's in YouTube. So I hope you don't mind. People can go there and watch again. So some people are asking whether they could have the presentation, but it's already there in the YouTube. So I'll send them the link. And many of the attendants are saying thank you in the chat here. So,
very nice.
So thank you very much once again. Okay.
Thank you.
Bye.
Bye-bye. See you.
Bye now.